Hello everyone, my name is Jinzhong from Shanxi University. Today's title of my report is Suppression of Noise-Induced Critical Transitions, a Linear Augmentation Method. The outline of this report consists of 5 parts. The first part is the background and motivation. It is known that critical transitions are widespread in practical systems. They refer to abrupt change from one dynamical system to another contrasting one. For example, in ecosystem, in aerospace, in financial crisis, or in physiology. Many of these examples only count one critical transition between two adjacent stable states. Typically, one of the stable state is desirable, and the critical transition leading to the other stable state is undesirable. However, multiple critical transitions may also exist. For example, in a disease development process, the cells undergo 3 states, including normal state, pre-disease state, and disease state. In fact, many practical systems are usually convoluted with stochastic perturbations. So, how do stochastic perturbations affect critical transitions? For simplicity of illustration, an example with only one critical transition in a stochastic complex system is shown in Figure 1. Here, alpha is the country parameter, beta is a promotion, and sigma represents noise intensity. It is found that a sudden bifurcation-induced critical transition to a contrasting undesirable state occurs at alpha 1 in the absence of noise. However, the noise can induce this critical transition to take place early, before alpha 1, alpha less than alpha 1, when the corresponding bifurcation is impending, which are more catastrophic. At present, the investigation on noise-induced critical transitions mainly focus on 2 aspects: early warning and suppression and control of them. About early warning, we have done some work, especially a new concept, parameter-dependent basin of the unsafe regime, has been proposed. This is an efficient tool to quantify the range of the country parameter where noise-induced critical transitions may occur. In this report, we try to achieve the suppression of noise-induced critical transitions. About country measures, there are adaptive country, sliding mode country, time delay feedback country, and so on. Here, a linear augmentation method is introduced to suppress critical transitions induced by Gaussian white noise from a new perspective. This country is designed in such a way that as a noise-induced critical transition is impeding, the desirable state in a stochastic complex system can be stabilized using a specific type of coupling with a linear dynamical system, as shown in equation 2. Here, epsilon depicts the coupling strength, y describes the dynamics of the linear system, and k its rate. Gamma is another important parameter, which is used to target the desirable state. With a proper trace of gamma and epsilon, the noise system can still stay in the desirable state even when the critical transition is impeding. Here we choose gamma close to the location of the desirable state. See, for example, see gamma equal xs1. One can achieve the disappearance of the undesirable state. Then we can suppress the noise-induced critical transitions. Different from other country methods, the linear augmentation method is an external country and don't change the internal parameters of the stochastic complex system. To further verify the effectiveness of this country strategy, the escape property of uncomparable system is introduced as an evolution method here. For the noise-induced one critical transition, like in this figure, The escape property is defined as shown in equation 3. By comparing the escape properties under different epsilon OK, the perceived effect on noise-induced critical transitions can be uncovered. In following, we demonstrated this method with two examples. The first is a bistable system with one critical transition. As shown in equation 4, when epsilon equals 0, the dynamic system for is shown in figure 2. The desirable state and the undesirable state are located around two stable points, xs1 and xs2, respectively. Although, as shown in figure 8, although the potential field of xs1 is shallow when alpha equals 0.62, the system has no critical transition to the desirable state in the absence of noise. When sigma equals 0.01, the trajectory is more likely around xs2 and the SPDF appears unimodal with most of the density concentrated around xs1. In other words, a critical transition to the undesirable state can be easily induced in the presence of noise. Next, we study the effects of the coupling stress epsilon on the expression of the noise-induced critical transition. Obviously, with the increasing of epsilon, this coupling method has indeed the ability to suppress impeding critical transition, ensuring that the system stays in the desirable state even in the presence of noise. Furthermore, the effects of the decreased K on the suppression of the noise-induced critical transition are also investigated. When K is smaller, the SPDF is unimodal with almost all the density concentrated around the xs1. However, gradually increasing K is not suitable to suppress the noise-induced critical transition to the undesirable state. Using the escape probability, the reverse effects of epsilon and K on the suppression of noise-induced critical transitions can be further verified. The second example is a tri-stable system with two critical transitions. The former is shown in equation 5. Previously, under small fluctuations, sigma equals 0.01, the critical transition 1 from the desirable state to the sub-desirable state can be easily induced. When sigma is further increasing to sigma equal 0.1, the critical transition 2 from the sub-desirable state to the undesirable state occurs. Therefore, the uncoupled system under strong fluctuations, for example, sigma equal 0.1, the system can shift from the desirable state to the undesirable state through CT1 and CT2 to ensure that system 5 can still stay in the desirable state in case of strong fluctuations. In case of sigma equal 0.1, the proposed country structure does not only need to eliminate the sub-desirable state, but also to eliminate the undesirable state. In figure 7, the effects of the coupling stress epsilon on the suppression of the noise-induced critical transition are investigated. It is found that the suppression of the noise-induced critical transition from the desirable state to the undesirable state can be achieved with the increasing epsilon. However, as shown in figure 8, gradually increasing K is not suitable to suppress the noise-induced critical transition from the desirable state to the undesirable state. To further verify the effectiveness of this country structure, The escape probabilities of system 5 against epsilon and k are given in figure 9. In figure A, we can find that the increasing epsilon first spreads the occurrence of noise-induced critical 2 and then spreads the occurrence of noise-induced critical 1. In figure B, it is found that the smaller k fail to spread the noise-induced critical transition 1, but can prevent the system from transiting to the undesirable state, while the large k gradually invalidated the suppression of noise-induced critical 2. All results are consistent with the results in figure 8 and figure 7. Finally, some conclusions are presented. The first, the linear augmentation method can spread these noise-induced critical transitions by annihilating the undesirable state. Second, two important parameters, the coupling strength and the decay rate, induce opposite effects. Third, it is desirable to if we can explore the coupling mode of high-dimensional systems with linear country systems. Yes, that's all. Thank you very much. Thanks for your attention.